Hi, my name is Naved, and today I want to talk about a recent work with Amir Ali Agazadeh, Tony Tu, and Kannan Ramachandran called Spectral Regularization Allows for Data-frugal Learning over Combinatorial Spaces. This work was accepted to the Transactions on Machine Learning Research. So the motivation for the problem comes from a problem that's commonly observed in biology, which is learning of a mapping from discrete spaces to real numbers. You can think about it as an example as genotype to phenotype mapping, where you're mapping strings over a discrete alphabet to a real number, which is as defined by the number f, the function f over here. And so when the inputs happen to be binary, this is called a pseudo Boolean function. And so this corresponds to the case where there are binary mutations, for example, in a protein. And you can always represent this function in its spectral form, which corresponds to a multilinear polynomial with 2 to the d coefficients. And so it's a degree d polynomial. So the dimensionality of the problem is basically 2 to the d. And learning such functions in practice is very difficult even for moderate values of d. This presents severe challenges both in terms of the sample cost as well as the computational cost. While these functions are commonly observed in practice, this is a barrier to learning them. And so what do you do to resolve this? And this is sort of the motivation for our work. So one thing that's observed a lot in practice is, pseudo Boolean functions in the wild. They often admit sparse representations in the spectral domain. And so if you think about it as this polynomial form, it only has a few non-zero coefficients. And here, for example, you can think about this plot over here, which plots, the function, which is the protein mutation pattern on a parent protein. And the y-axis is the value of the function here, which corresponds to the brightness. And so you observe this function being sparse, it only has a few non-zero coefficients. In the plot below, you can see only a few spikes, which corresponds to the coefficients. And these can also be interpreted as the degree of interaction between, various protein, the mutation sites in the protein. So given that these polynomials admit sparse representations, it leads to a natural algorithm, which is what we call spectral regularization. So this composed of two terms. The first one is basically the mean squared error over n samples. And so this is g subscript theta is the learned function over here. And so the first term corresponds to the empirical risk evaluated on the data set that you have. But on the other hand, you want to bias these functions to be sparse, because you know that the ground truth function is also going to be sparse. And so to that, you add a term which is called the sparse spectral regularization, which corresponds to a Walsh-Hadamard transform of the function. So h of g theta of x, this corresponds to evaluating the spectral form or the polynomial form of the function, and you evaluate its L1 form. And so this is computed over all 2 to the d enumerations of the binary input sequences. Now it turns out that for this algorithm, for learning a function g subscript theta star, so this is a realizability assumption on the true function, and you assume that it's also k sparse, so the number k over here is the k sparsity. Under some mild assumptions on the loss function, being satisfying the restricted secant inequality, turns out that choosing this regularization parameter lambda carefully, and also as long as the data set is like sufficiently large, scaling as d cube plus order dk, if you compute any first order stationary point of the empirical risk with spectral regularization, so this is basically the previous on the previous slide as defined, with high probability you're going to output a parameter, or so you're going to learn a function which is very close to the ground truth. And so how close it is sort of scales as square root kd over n, which also turns out to be optimal in a statistical sense. So this is the first result that we have in the paper, and this relies on the restricted secant inequality, which basically says that the gradient of your particular function is correlated with the direction to the optimal solution. And so we have imposed this function on the loss function, and so this is saying that gradients are indicative of the direction to the optimal solution. But what happens when the gradients are not indicative? And this is what you would expect to happen more typically in practice, even though this covers a wide family of functions already. They remodel what is called a quadratic growth condition, which is a much weaker condition. All this says is around the point theta star, the loss is locally bowl-shaped, And so it just says that it grows quadratically, at least quadratically around the point theta star. And over here, we show a slightly different result. And so under, the same like quadratic growth assumption on the loss, and a smoothness condition on the functions g theta that you're parameterized with, choosing your regularization properly and with a sufficiently large data set, any first order interpolator of the empirical risk with spectral regularization is good. It's close to the ground truth function. And approximate first order interpolator is defined as a point that has a small gradient, and at the same time, it approximately interpolates the training data. So its training loss is small. And when you train, for example, a neural network in practice, these are the kind of points that you usually output, because the neural network will do what is called benign overfitting, and it learns to approximately interpolate the data set that you have, just by virtue of being highly overparameterized. So moving on, the experimental results very quick. It turns out that having this spectral regularization actually improves the generalization performance. And so if you look at the x-axis, these are 4 different algorithms: mean square error plus spectral regularization, just the mean square error. So you run gradient descent on the mean square error, and the mean square error plus L2 and L1 loss on the parameter vector of the neural network. It turns out that in all the 3 cases, which are 3 different data sets, a protein data set, T-cell data set, and a cancer data set, having the spectral regularization actually improves the generalization error, uniformly. And so these are on depth for neural networks. So these are, highly nonlinear functions, highly nonlinear architectures. And so it's a sort of like an empirical evidence that spectral regularization improves the generalization error. Another plot that you can have over here is just comparing spectral regularization without spectral regularization. So what's the effect of this? And so here is a function of the number of samples, the size of the data set. And so if you look at 3 columns, each of the top plots, this corresponds to just without any regularization. And so the blue curve, or the blue region of each curve, corresponds to where the loss is very small. The algorithm is doing very well. And so in each of these plots, you can see that the blue region is larger at the bottom, which means that the spectral regularization is actually performing better. And so it works in a larger range of parameters. Here where it's monomial, power law, or staircase, these are the kind of sparsity patterns that you have in the ground truth function. Shows that spectral regularization works better across all of these patterns. Another final plot that we have is like a quick experimental evaluation of this quadratic growth condition, showing that it actually might be satisfied in the case of neural networks. And so I won't go into too much detail about the estimation method for this quadratic growth condition, because it's not easy to explain very quickly. But you can see that somehow the estimate never goes too close to 0. It's always bounded somewhere between 10, or and for depending on the training round, it could be even larger. And so this is again across 2 fully connected different architectures, and so this is again sort of like a reason to believe that the quadratic growth condition will be true in practice. So finally, just a quick summary: it's a natural regularization method for learning sparse pseudo-Boolean functions. There are some theoretical guarantees under growth assumptions on the loss, and a lot of promising experimental results in showing an improvement in generalization across data sets, and hopefully this can be implemented across larger data sets and for larger problem sizes. Our paper is on arXiv, and with that, I'll end. Thank you for your attention.